It is my pleasure to introduce the Gobler, who's going to talk to us about numbers.
Thank you, Jim. Welcome, everyone. So I am really excited to tell you today about tangles and have this be your first introduction. This is one of my favorite things to talk about. We're going to discover some things together, and I think you'll be really amazed with the results. So let's get right into it. But first, I wanted to say I prepared a bunch of speaker notes, but they're not really for me. They're for you. If you enjoy the talk and you want after, just I'd like to share these with you. So let me know after the talk. I can send these to you. So if you just want a clean copy of notes, you don't have to write anything down. But there will be a chance during the talk to do some calculations. So if you have paper and you want to do that, that would be great. Okay, so we're going to talk about tangles, and so to do that, I brought with me these two ropes. But I'm going to need some volunteers to hold the ends of the ropes. So can I ask for some volunteers who are going to come stand here and do the tangles? Because there's 4 volunteers. Yeah, okay, great. Thanks. How many hands do I need? I guess just one. Yeah. Okay, yeah. One more volunteer. Don't be shy. Just you'll be up here for maybe 10 minutes. Sam, and what's your name? Brooke. Okay, so Brooke. And Brooke. Okay, great. Okay, so you're actually, this is perfect. So you're already standing in position. So we can make sure that would you mind could you take a few steps toward the board? Great. So we'll see that. Okay, great. Yeah. So you're all right. So the first thing that we should do here is I'm going to share with you, or we're going to just talk about how to make a tangle. And the first tangling move is called the twist. So to do the twist, the people who are standing in this position, so you'll do the twist. Okay, and it starts like this. The person who's in this front corner is going to raise their right eye. Okay, and then the back corner is going to go underneath, and we'll swap places, and that is the twist. Okay. All right. Okay, let's have another twist. Other twist. So we raise and all right. So now there are 2 twists in the rope, and now so the audience can see better. We'll have this present. So to do the present, the people in front will hold low, and the people in the back. Yeah, there we go. So now you can all see the tangle. So let's pick them up. Yeah. All right. So now, and by the way, I should say you'll want to people up here. You'll want to pay attention to the moves because at some point you might be in these positions. All right, but for now, we have a seat here. So thanks. Oh, and yeah. So okay. Okay, so we have the and in case it's hard to see, I also want to draw some pictures. So here's what has happened. We started with the ropes like this. So this will always be the starting configuration. Always start from the pair of ropes being parallel to each other and I guess horizontal to the audience. Then we did a twist. And after the twist, the ropes look like this. And when I draw like this, I'm trying to show you which rope is above and which rope is below to the audience's perspective. All right, and then there was another twist. Like this. Okay, so in order to talk about these things, we're going to have some sort of notation here. And so this isn't the mathematician's spirit, really, of giving names to things. We're going to do exactly that. So the starting configuration, we're going to call 0. So the names here are just numbers. Okay, so the starting configuration, is called 0. So the 0 tangle. Okay, and then we'll call this tangle 1 tangle, and this tangle the 2 tangle, and so on. So when you twist, the tangle number increases by 1. The twist adds 1. Twist adds 1 to the tangle number. Okay, so here's the tangle picture. Tangle picture, and then below it, I'm writing the tangle number. Tangle number. And we can also describe the tangles in terms of the movements that it took to create them. And so for the twist, I'll just use a capital T. So this tangle is just 1 twist. Okay. This tangle is 2 twists, which we could write TT, or we'll also just abbreviate T squared. So these are the tangle words. Here I'm putting the tangle words. Okay, so we have tangle pictures. To each picture, we assign a number, the tangle number. Okay, the starting configuration has tangle number 0. That's a 0 tangle. And then every time you twist, you add 1. The twist adds 1. Okay, we get the 1 tangle, the 2 tangle, and you can keep twisting. You'll get a tangle for every natural number, including 0. Okay, so that's a lot of things. Now, what about negative number tangles? A natural question. Can a tangle have a negative tangle number? Okay, so that's right. So if you twist the ropes the other way, so if you do an untwist, then when you twist the ropes again, you've undone what you did before. Okay, but I think I can draw exactly what that looks like. So let me start another picture. So here's the 0 tangle, and you can imagine what kind of tangle would have to be so that when you twist, you get the 0 tangle, right? And that would naturally be the -1 tangle since the twist adds 1. Right? And it would look like this. And there's also a -2 tangle, which looks like this. And can you tell the difference between these sets of pictures? So they're very similar. So what's different about the 1 tangle and the -1 tangle? Can you say?
One is above.
Yeah, which one is above? Yeah, that's right. So the overstrand, what we'll call it, the overstrand, the strand that the rope that's in front has changed. So there's a nice way to keep track of that. At each crossing. So if the crossing looks like this, right here the overstrand is making a positive slope, right? And so this type of crossing is called positive. This is just a convention. And the crossings that look like this, with the overstrand making a negative slope, we'll call negative. We have positive and negative crossings. And yeah, so now we can describe the difference carefully. So the positive number tangles have positive crossings, and the negative tangles have negative crossings. And then the only difference between, say, the 2 tangle and the -2 tangle is that you've changed the crossings. So already there's an observation that you can find the negative of a tangle by just switching the crossings for negative, and vice versa. Okay, but as for making the negative tangles, so we could make untwist. So that would be the twist, but the other way around. But for now, we're going to only allow ourselves to make positive twists, just the regular twists. So if that's the case, then we don't yet have a way to make these tangles. But that's okay. Instead of allowing ourselves untwist, let's introduce the second type of tangling move. So I'll need you back up again. Okay. So you just untangle. No, this is okay. So right now there's 2 twists in the ropes. There are 2 twists. Okay. Now the second type of tangling move is called the rotate. And to do a rotate, we'll have all 4 people trade places one place around counterclockwise. So you'll go here and across. So let's spin and stop. Okay, and that's a rotate. And can you present? So people in the front will go down, and yeah, can you see now? So the stack of twists is vertical. Okay, great. Let's have another rotate. All right. Okay, great. Thanks. Yeah, and now the question is this. So what tangle is in the ropes? Well, there were two twists, so it's probably either 2 or -2. Can you figure out which one? It might not be obvious. How could we check? How could we test to find out? Any suggestions?
For either positive or negative flips.
Yeah, so maybe it's harder to see from the back, but the rope holders, can you tell if the crossings are positive or negative? Yeah, you're right, they are positive. In fact, we could check by twisting, right? If this is -2, we should expect that if you twist, you'll get to 0. Should we try that? Can we have another twist? So
He goes over.
So yeah, so you'll raise your rope and then Sam will go under. Okay, so does that look like 3 or -1? Can you tell us?
No, it's like
Oh, okay. Yeah, so it really was +2. Okay, so we started with 2 twists in the rope. We rotated twice and still had +2 twists in the rope. So what we really were demonstrating here is a symmetry of the helix. The helix has a rotational symmetry. And the difference between the 2 tangle and the -2 tangle is that they're mirror images of each other. So to get one from the other, you would have to look in a mirror, right? Not rotating. Okay, so we still haven't been able to make a -2 tangle. That's okay. A more important question though is what does rotate do to the tangle number? So I said twist adds 1, but what about rotate? So let's see if we can figure that out together experimentally. How could we do that? Well, let's see if we can figure out what rotate does to some small tangles. Say we could start with the 1 tangle and then the 2 tangle and see if we can figure out what it is. So let's reset the ropes. Can we, oh yeah, we can just untwist. Great, thanks. Great, okay, you're doing very well. So the goal now is to figure out what does rotate do to the tangle number. So let's start testing this on the 1 tangle. So let's have 1 twist. Very good. Okay, and now rotate. So rotate. And can you present? So let's see. So can the audience tell what tangle is in the ropes right now?
Negatives. Good one.
Is it one or -1? Can you tell?
-1.
Yeah, that's right. So the overstrain is negative. Yeah, so rotate turns 1 into -1. So can I just step behind you? Great. Okay, so let's just keep a document of this. So if you have the 1 tangle and you rotate, you get -1. Okay, and we rotate again. Okay, and present. And now we have, and now what tangle is in the ropes? Can you tell?
+1.
Yeah, so that's the 1 tangle. Okay, so rotate from -1 to 1. Okay, and we were expecting that because it seems like when you rotate twice, nothing happens. And you might wonder if that's true in general. If once we make really complicated tangles, if rotating twice also does nothing, or maybe it will start to have an effect. So it turns out actually that yes, when you rotate twice, it's the same as doing nothing, but that's maybe hard to see why. I don't think we're going to talk about it, but there is a really nice reason, and it just highlights something beautiful about the structure of these tangles. I guess we won't get to talk about that today, so you'll have to take my word that 2 rotates does nothing. Okay, but at least now we have some data, right, which informs us something about the effect of rotate. So now I'd like to hear from you. There are 2 data points. Can anyone make a conjecture about the effect of rotate on a tangle number? So if you're trying to draw a pattern here, Any guesses? Any guesses so far as to what rotate does to the tangle number? Just guesses? So you don't. Yeah.
Odd rotation negates it, and even rotation keeps it the same.
Excellent. Okay, so conjecture that rotate negates the tangle number. Thank you. Any other conjectures?
-1 to the nth power.
Thank you. Yeah, so maybe rotate exponentiates the tangle number. That was the suggestion. Great. Okay, it's possible. We can't know. Yes. So let's test both of those conjectures on the two tangle. So let's try that. So can we have another twist? Okay. Great. So now there are two twists in the rope, and let's rotate. Okay, so, oh yeah, and you present, so you've seen this one before. What is that? What is this tangle? Actually, I'm gonna come through here. I just wanted to draw this on the board. So we had the two tangle, and then we did rotate, and now we're looking at something like this. Right? All right, and this is a tangle that we haven't assigned a number to yet. Okay, so now it's a mystery. Let's call it X. Okay. So how will we find the value of X? Well, we'll have to do some sort of alchemy here and try to test out some moves on the ropes. So our choices are we can twist or we can rotate. Now I declared that if you rotate twice, it does nothing. So if we rotate again, we'll see two. We already know that. So how about we try a twist? So let's twist. Okay. Aha, and what happens? Let's present. Yeah, so look at this. Okay. It looks very similar. So is this the same? Or can you tell? No, this is subtle. It looks very similar to the tangle X, except the picture now looks like this. That was a twist. Okay, so what changed? What changed?
Which one's the top row?
Yeah, so yeah, here this was the top row. Okay. Yeah, so the crossings have changed, right? So the crossings changed, both of them. Okay, so this angle must be negative X. Okay, and let's see, we could twist again, or we could rotate. What should we try? So your suggestions here. Should we twist or rotate?
Rotate.
Okay, let's rotate. Yeah, so go ahead, so rotate. Okay, and now what is the tangle? You see? Yeah, that's right. So it's the -2 tangle. We've seen this before, and you know what happens when you make two twists, right? So let's have two more twists. And okay, that's 1 and 2, and the ropes are untangled. Okay, very nice. Yeah, let's applaud the. Great. Okay, so we have a bit of a story here. We know just a little bit more about this tangle X. Now, the goal was to figure out what number is X. And is this enough? Have we learned enough about the tangles to deduce the tangle number? It might not seem like it, but the key is here. We did a twist, and you remember how twist affects the tangle number, right? Twist adds 1. Okay, so it should be that when you take X and you add 1, you get -X. So we can solve for X. Let's solve for X. Okay, so it looks so here you get 2X -1. So it is, what do you know? -1/2. Okay, who was expecting that? Okay, that's pretty amazing, right? So this tangle here has tangle number -1/2. Okay, and that means that tangle with negative x has tangle number -1/2. Okay. Wow. Okay, just from this one twist alone, we could figure that out. Okay, so now we have more data. Here was a rotate. So rotate takes 2 to -1/2, and also takes +1/2 to -2. Okay, so we're learning a little bit more about rotate. And it looks like this might have broken the conjectures we made earlier, right? So when we rotated 2, we did not get -2, so we got the negation. But is this enough to see another pattern? Yeah.
It's the negative inverse.
Oh, great. Yeah, so negative inverse, right? It is having that effect, right? So here's the opposite reciprocal of 2 is -1/2, and same for 1 and -1, right? That's pretty cool, right? So I say we should challenge this new conjecture on another tangle. How about the 3 tangle? We did 1 and 2. So let's have 3 more twists. Okay, I'm going to start erasing. All right, so we have the 3 tangle in the rows, and our goal now is to untangle. So the audience, I'd really appreciate if you want to make the suggestions here. So we're exploring together. We can get this wrong. So a suggestion, what to do first. Yeah. Here's the 3 tangle. What should we do? Twist or rotate? Rotate. Okay, let's rotate. Now. Okay, now we have, look at that. So the twists are vertically stacked. So if our hypothesis is correct, this should be, so what is the tangle number here? 1/3. Okay, -1/3, so the opposite reciprocal. Now what? So should we twist or rotate? Okay, yeah, that's a good idea. So if we rotate twice, nothing happens. So let's have a twist. Okay. Wow. Yeah. And can you present that? Yeah, let's see. So look at this. Can you see? Let me draw. So okay, so we just had a twist, but now we're looking at something like this. Okay, whoa. Okay, but what's the tangle number? Sorry. Yes, that's right. So add 1. So here's 2/3. Now, question: should we twist again or rotate? If we twist, we'll see 5/3. If we rotate, we'll see -3/2. Your choice. Twist or rotate.
Okay.
Why rotate?
Because you said we want to challenge this if we would like to get if you want to get, because that will give us like -3 pounds. So that's interesting.
Okay, sure. So let's do -3/2 with a rotate. So rotate. I'm gonna get that new column here, right? So you rotate, and now it's something like yes. And the tangle number is -3/2. Okay, we just did a rotate. What next? Twist. All right, let's twist. And what happens? Oh yeah, see, here's a negative crossing, right? That I drew. And so you twist, and this now clarifies, right? So you twist, and now the picture looks like this. Okay, tangle number. -1/2. Oh, we've seen this before, right? We know what to do now. What next? Rotate. Okay, so if we rotate, so let's rotate. And now in the rotate, the tangle number is 2. Okay, did we want that? We want 2. What's the other way? So we only have positive twists. Okay, so maybe that wasn't exactly what we wanted. Will you rotate back? So if instead we do a twist, now from -1/2 we get positive 1/2. Okay, and then a rotate. And now, what's the tangle number? -2. Okay, and that's better, right? That's better because now we can twist. So let's have the 2 more twists. And the ropes are untangled. Right? Excellent. Okay. Very good. Very good. Okay, so it seems to be working, right? So we had some more complicated fractions here, but it seems like our theory has matched what happens in practice in the ropes. But this time we actually had to be a little more strategic. Like for example, we had to make a choice here at 2/3 whether to twist or to rotate. Now, if you now how did we know to rotate instead of twisting again? So if you twist again, so you get 5/3 versus -3/2, well maybe -3/2 seems simpler. But if you needed a like a rule for when to twist and when to rotate, how would you decide? Let me finish the sequence. So after -1/2, there was a twist for 1/2, then a rotate to -2, and then a twist, 2 twists to 0. Okay, so we went 3, rotate. So -1/3, twist to 2/3, rotate to -3/2, and then twist, all the way up to positive 1/2. Then a rotate and 2. Okay, so what happened here? How did you know? Yeah, go ahead.
Do you twist until you get greater than 0 and then rotate and twist once you get greater than? That's kind of what we seem working on for.
Yeah, that's great. So it does seem like once we reach a positive number, then we did rotate. And that's good because otherwise if we did another twist and saw 5/3, an even more positive number, it does seem like that would have been larger to work with. So as maybe our first iteration of the strategy, it's not a bad idea. So let me just say again what Sam said, which is just if the tangle number is negative, twist as many times until the tangle number is positive, and then rotate, the tangle number becomes negative, and repeat. So twist if it's negative, rotate if it's positive. This is really not a bad idea. And I think if you're willing, I say we put this strategy to the test with a blind faith challenge. Should we do it?
Yeah.
Okay, so let's make a larger tangle, and I have one written out already. So this is going to be the biggest tangle we've made so far. Okay, are you ready?
Yeah.
Okay, so first let's have 2 twists. And by the way, if you have paper in front of you and you want to keep track now of the tangle number, that'd be great. So I guess I'll do it as well on the board, but I'd like you to try this also. Right. So we started with 0, and that was 2 twists. So the tangle number is 2. Okay, and let's rotate. And now let's have 4 twists. 4 twists. 3 and 4, very good. Okay, the tangle number now, 7 halves. And let's rotate. Okay, so now -2 7s. And now another 2 twists. 2 more twists. Okay. What's the tangle number? 12 sevens. From the audience, or sorry,
12 sevens.
12 sevens. Okay, 12 sevens, and rotate. Okay, that's -7 12, and 2 more twists. 2 more twists. Okay. 2 more twists, and the tangle number now. Very good, yeah, so, okay, 17 12s, and one more rotate, that's all. Rotate, so now we're looking at minus 12 17, and can you display that? So present, look at this math. Okay, so we've made a pretty vicious tangle here. Now we're about to untangle it together using that strategy, but to raise the suspense, I brought a bag. We're going to cover the tangle. So keep this a mystery until the end, okay? So can I have you ready? All right, so. Oh, put this into the bag. Okay, and now I'm going to just cover this here and tie it together. Okay, so I just hope this doesn't. Okay, so the knot's in there, or the tangle rather. The tangle is in there. Let's untangle it, but this time we're doing it blindly. So we'll have to let the mathematics guide us here. All right. So what do we do? So the tangle number here is minus 12 17. Let's untangle it together, but I'm going to ask you what to do. So let's start. We're at minus 12 17. What should we do next?
Twist.
Okay, let's twist. The tangle number?
5.
Sorry, I can't. Okay, you have to speak up. Thanks.
5 over 17.
5, okay, 5 over 17. What next? Let's rotate. Okay, and now minus 17 fifths, and let's
Twist.
twist
4 times.
4 twists. Okay, 4 twists. Very good. So twist 4 times, and the tangle number now is 3 fifths. Okay. Someone's watching them, right? They're doing all right, and let's rotate. Rotate, so now minus 5 thirds. Audience.
Twist twice.
2 twists. Okay, let's have 2 twists. So I'm glad you can all do the calculations here. So 2 twists, and where are we now? Positive. Okay, positive 1/3. Remember what it says, and now let's rotate. So that's minus 3. Okay, we know what to do for minus 3. Let's have 3 more twists. Okay, that's the last of it, right? Great. So supposedly now we're looking at the zero tangle, right? So let's find out. So a drum roll. Okay, I was so excited. I'm gonna rip it apart. So let's find out here. Okay, so the bag, check this out. All right. There it goes. And shake. And okay, there it goes, shake. All right, you know it works. Right? Very good. So that's all for the demonstration. So I'll take the road back. Let's have one more round of applause. Yeah. Okay, so it works. By the way, so this demonstration is inspired by something Tom Davis does. He runs a math circle, and so if you're interested in these kinds of curiosities and experiments, you should look into his work online. But I just want to pause here. So that's about a little more than half of the talk, and I think this would be a good chance to just reflect on what's happened so far. Okay, so we started by defining the tangling, the valid tangling moves, the twist and the rotate. And we use those to assign numbers to the tangles. The twist adds, we start with 0. The starting tangle is the 0 tangle. Twist adds 1. We found together that rotate has the effect of the opposite reciprocal to tangle numbers. Okay, these are just conjectures, but it seemed to work in a very complicated tangle, so that's already promising. It's incredible. There's such simple rules, right? To add 1 and opposite reciprocal, and it seems that's enough to untangle the ropes. I just want to stress this point. So we we started with a complicated tangle. We were able to untangle it using only twist and rotate, only the positive twist and rotate. And I think probably that would have been surprising to you at first when we started with just the integer, the whole number tangles. You would have thought that in order to untangle 3, you would need to do untwists. But using our strategy, we're able to untwist the ropes using still the positive twist. You think you just keep doing positive twists and somehow it actually simplifies in the end. That's a pretty incredible thing. I want us to appreciate that before we move on from it. And for the group theorists in the audience, what we're saying is using the strategy is that the tangle words have inverses. You start with tangle word, append another tangle word, and get the untangled. And so that means that the set of tangles forms a group. And you might now wonder, what is the structure of that group generated by twist and rotate? So it's an infinite group. What is its structure? Maybe leave that for now as something for you to think about, but maybe I can answer that later if you'd like. All right, so it's a big claim I'm making. Every tangle can be untangled using only positive twist and rotate. And we had a really nice strategy to do this, but it's worth better understanding the mathematics behind our strategy to just I guess settle in that it's a working strategy. So what I mean by that is it's possible using the strategy of twisting when negative and rotate when positive. It's possible that could get us into a loop, right? Or worse, maybe the tangles will get uncontrollably tangled. If we're not careful, right? So how should we know that this will work every time? It really is worth thinking a little bit more about the mathematics behind the strategy. So let's do that next. All right. So what happened in this last example? So let's focus again on how this calculation went. We started with the tangle number minus 12/17. It's negative, so we were going to twist until negative 12/17 became positive. Right, twist until it becomes positive. So that means we're going to add 1 to minus 12/17 until it becomes positive. And if you were doing the calculations, you might have noticed something funny happens when you add 1 to a fraction. When you add 1 to a fraction, like minus 12/17, it's just like adding the denominator to the numerator. This is when you find the common denominator, it just happens to work out this way. That really what we're doing is adding 17 to minus 12 until it becomes positive. So what we're doing is this. So add 17 to minus 12 until it becomes positive. But there's something equivalent, sort of in a mirror world. We can flip this around, and this is really the same process as subtracting 17 from positive 12 until it becomes negative. So what I mean is this is really the same path as this, which is subtract 17 from positive 12 until it becomes negative. So these are really the same thing in a mirror. But the reason I have this rephrasing is because I think that this will be a little more familiar to you. So first, you subtract 17 from 12 until it becomes negative. So in our procedure here, that happened once. You subtract 17 from 12 once, and already it's negative 5. All right, I can summarize that with an equation. It looks like this. Okay, 12 is 117. 12 is 17 minus 5. Right? Okay, you knew that already. But the way to interpret that is you have 12, and if you take away 117 from 12, you'll get minus 5. Okay, and then the rotate happens, and the numbers switch places, and now you're adding 5 to negative 17. Okay, so this process repeats again with 417. So you subtract, in this mirror version, you subtract 5 from 17 until it becomes negative. So you can do that 4 times, and you'll get minus 3. Okay, and this repeats again. So after the rotate, the numbers switch places, and I can finish this here. So it goes, so 5 is 2 3s, so subtract 3 twice, and you'll get -1. And finally, 3 is 3 1s. But this time you didn't overshoot. We get exactly 0. And that's when we reach the 0 tangle. Okay, and the ropes are untangled. Okay, and you see the number of twists are appearing right here. This is how many, the multiples here are how many times you twist, how many times you add 1. Okay, so some people are smiling. So if you were in the algebra class this morning, you'll recognize this. It looks a lot like the very famous Euclidean algorithm for the division of integers, the GCD algorithm. And it's very similar and the way the algorithm works. So if you are familiar, it's exactly this. So you have numbers like, let's see, 17 and 5. 0. So 17. So every time you subtract 5 from 17, you're hopping along the line. Okay, so the picture isn't perfect. Okay. So usually in the Euclidean algorithm, you stop when you get closer to 0 than the number you're subtracting, 5. But in our version, we overshoot by 1. So 1 extra hop. This is like, maybe you could call this the greedy Euclidean algorithm, because it's just a little bit greedy. When the remainder is small, you hop anyway and take more. Okay. But it turns out this is really just the same as the Euclidean algorithm, or it has the same effect. The Euclidean algorithm famously terminates very quickly. And so in some sense, this is enough to justify our strategy's success. So the correctness of the Euclidean algorithm says, yes, the strategy we use to untangle the ropes will work every time. Not only that, it's famously quick. It's very efficient. So we just happened to guess the perfect strategy. That's awesome. We just stumbled into that. Okay. But the mathematics behind it is something very famous. And I guess I could say too, it's simple enough. So really, it's just subtractions. So if you had to predict before the talk started what kind of mathematics governs the complex nature of tangles of ropes, you probably would have thought something very difficult, right? If I claimed that there was some mathematical process which could keep track of the state of the tangle at all times, you say, gosh, it's probably some calculus, topology, something crazy, right? Nope, it is just subtraction. It's just this kind of arithmetic that you could probably do in your head. It's really incredible. Yeah, and I have a couple more things to say here. So you might know, if you're familiar with the Euclidean algorithm, that it's related to the process of building continued fractions. I'd like to show you that next. Okay, so how does that work? Well, see this. If you start with 12 17ths, then the first line of the algorithm says you can rewrite 12 as 117 minus 5. So let's do that. So 117 5. Okay. Okay, and then this fraction we can split into two terms. The first term is the 17th cancel, so it's 1, and the second term 5. Okay, natural. And then the next step is more artificial, and it's to take this fraction and invert its reciprocal. So that looks like this: 1 over 17/5. But now 17/5, we can rewrite 17 using the next line of the algorithm. So now we have 1 minus 1 over, and 17 is actually 4 5s minus 3. 4 5s minus 3, yes, over 5. Okay, and we're doing this again. So let's break this into two terms. It's 4 minus 3/5. Okay, and then reciprocate, so that's 1 over 5/3. Okay, and then rewrite 5 as, so I'm erasing to do this. So write 5 as 2 3s minus 1. and split the terms again, and you'll find it's 2 and a 3. Okay, and we're done. Okay, so the steps are instructing you how to turn this fraction 12/17 into a continued fraction. So this is a continued fraction, which is maybe more exotic than the ones you see. Here, all the terms are negative, and that's okay. But really, what's important is that the coefficients here are 1, 4, 2, and 3. The coefficients of the continued fraction are just the number of twists. And I also want to say that this is something that we could have seen long ago if we had been more careful and didn't choose to reduce the tangle numbers at every step. So what do I mean? So this tangle is, I'm getting a little messy here. So this is the tangle, which starts with 3 twists and then a rotate, and then 2 twists and then rotate, 4 twists and then rotate, and finally there's 1 twist. Okay, so those are the movements we did to undo the mystery tangle. So we kept track of the tangle number together. Here's what happens if you don't simplify at each step. So you start with 0. And then we twist 3 times. The tangle number is 3. So add 3. Okay. Then rotate is opposite reciprocal. So we do that. And then 2 more twists adds 2. Okay. And rotate is opposite reciprocal. And then the next 4 twists is add 4. Okay. And then the next rotate is opposite reciprocal. Okay. And then the last twist is adds 1. Okay. So if you don't reduce the tangle number at every step, the most natural appearance of the tangle number is in this form as a continued fraction. It's something very natural. And this is great because the continued fraction tells you, I guess, 2 things at once. Now, let's see, I've made this a bit messy, but it's the same as this continued fraction. So look here instead. So I want to emphasize something about the continued fraction, which is really fun. It allows you to answer 2 types of questions. The first is, what is the tangle number of a given tangle? Okay. So here's a complicated tangle word. If you want to know the tangle number, just take the twists, write them as the coefficients of a continued fraction, and evaluate this. You'll get 12/17. Okay, but at the same time, if you can answer the reverse type of question, which is if you have a tangle number in mind, like say you're thinking of 12/17, and you want to make a tangle, the tangle which has tangle number 12/17, all you have to do is find a way to write 12/17 as a continued fraction like this, and you can do that using the 3D Euclidean algorithm. And once you've made this continued fraction, the coefficients tell you what twists to make. And you can twist up your rope exactly like this, 3, then rotate 2, then rotate 4, 1, and you'll make a tangle with the tangle number you want. So this kind of structure in the continued fraction is something that I get to appreciate in my research, which is that it acts as 2 things at the same time. It's a nice way of storing a sequence of numbers, but at the same time, it's a number. It has a rational value. So it's acting at the same time as, like I said, it's telling you something to do, movements to make, but also has value. And so it's just the most natural object to keep track of both these things. So I have one more point to make, which is this. I just claimed that if you want to find a tangle for this tangle number, all you have to do is write it as a continued fraction in this form. Okay, the problem with that is there might be more than one continued fraction whose value is 12/17 in this form. Okay, it isn't unique. And so the problem with that is that if we find 2 different continued fractions for the same number and we build their tangles, what if you get 2 different tangles? So that would be a problem. That would be like a clash in the namespace. You'd have 2 different tangles with the same tangle number. That would be problematic. It turns out that that's not the case. The answer is the nicest one you could possibly have, which is this. If you ever find 2 continued fractions for the same tangle number and you build tangles, those 2 tangles will be isotopes. they'll be exactly the same as each other. In the sense that, what I mean by that is if you pin down the corners and you just do some internal wiggling, you can turn one tangle to the other. That's just incredible, and I want to demonstrate that for you. And this will be the last thing. So I made an example here to show you. This is really just incredible. So I found 3 different ways to write the number -1 as a continued fraction in the form. Okay, one of them, you won't be surprised, it's -1. The next is 0 minus 1 over 2 minus 1 over 1. And can you check that? So 2 minus 1 is 1, and this is 0 minus 1 is -1. Okay, and here's the third. Just gonna use this last bit of room here. Okay, and the third is this. 1 minus 1 over 1 minus 1/2. Okay, so 1 minus 1/2 is a half. Reciprocate, you get 2, and 1 minus 2 is also -1. So what happens when you build tangles using these 3 continued fractions? I was going to draw it for you here in real time. To draw tangles with rotate, you sort of have to do it on a moving object, so you can draw and rotate and draw and rotate. That's hard to do on the board, but let me just draw for you what those tangles will look like. So here's the familiar -1 tangle, negative crossing. Okay, here's the tangle you get if you do 1 twist, rotate, 2 twists, rotate, and then 0 twists. You'll get this. And the last one here will look like this. That's some tangle. But you can sort of see here were the 2 twists, here's the 1, and here's the 1. So 2 twists, 1 twist, 1 twist is what happened. Okay, now I'm claiming that all of these tangles, although they look very different, are actually the same as each other. And how do you see that? Well, you're just supposed to pin down the endpoints. So just fix these in place and do some wiggling. So here, look, here's the overstrand twice. So this piece of rope we can just lift off, right? Here. And now you have, oh yeah, that's -1. Did you see that? Okay, so pretty cool. And what about this one? So maybe hard to remember, but look, there's this huge like handle here, right? This piece of rope that crosses 3 times. You could just take that and lift it up. And let me try to do that. I'm gonna lift this up here, right? And then you can see this just has a little bit of an internal rotation. So it looks like a positive crossing, but if you pull the ropes tight, you'll see that really is -1. Okay, it's just incredible. Now the result is due to John Conway. And so he's the one he wrote a paper with these results. And so sometimes rational tangles are referred to as Conway's rational tangles in his name. But this is just a really beautiful result because it means that the way we assign numbers to tangles is like this perfect encoding where anytime 2 tangles have the same tangle number, they really are just the same. So it's just this perfect environment. That's really something special to appreciate. So I hope you just find this really magical and fascinating. Thank you very much. Questions?
What's the name again? Did you say isotope or what did you say?
I said that these tangles are isotopes or isotopic. Isotopes. Now, I haven't really studied much in knot theory. Maybe if someone in the audience will know this terminology better. I think it's correct to say that.
Yeah, are we assigning a tangle to -infinity? I think it's 0 and then rotate.
Oh, that's a really great question. Yeah, so notice if you start with the 0 tangle and then you rotate, you get a tangle like this. And according to our naming system, this should be 1/0. And in fact, that's not such a crazy, that isn't a crazy thing, because you see what happens when you twist this tangle. So twist. Oh. So yeah, this is the tangle where you add one and get back the same tangle. And so in some ways, it's very natural to extend the rationals here by 1/0. So it's playing the role of infinity, compactified, like a plus and minus infinity. In fact, so my research, which involves continued fractions like these, it's a very natural thing to introduce 1/0 exactly like this. It behaves well in continued fractions where 0 is a coefficient. So the theory is actually resistant to something like this. It doesn't throw a wrench in things, but actually makes it more complete. Yeah, so thanks for asking. Yeah, Matt.
Yeah, I don't see who recognizes this group.
Okay, sure. So the algebraic structure is maybe tricky to identify already. Yeah, maybe keep thinking about that some more. But I promise it's a relevant group. It's very important. It appears many places in mathematics. So many areas in study of functions, study of
Did anybody else get it?
What?
There's gotta be, at least gotta be here who I've seen in my class. I want to see who.
Should we reveal?
I think, no, let's see if we can figure it out.
I only do it because that comes up in modular forms. So if you know the theory of modular forms, you do definitely know this group.
Yeah, and
Anyone who's staying right.
By the way,
Class has seen this.
so for the people who aren't algebraics or don't have this background, what you can still appreciate from this is that our fun little demo modeling or having like ropes tangle, it seems like just a party trick that we were able to untangle the ropes without seeing them. But the mathematics behind this is so relevant and important in the theory. So modular forms too. I had two or three examples I can think of. So if you talk about having a context for these things or like broader impacts. So this is actually something you can take away with you and will have some relevance the more you study mathematics. Or something that our grad students can change at a deeper level. Yeah, other questions? All right, thank you.
Club next week is my guess. Thanksgiving, everybody. See when that's all.